So in the previous lecture, we just saw surprises in high dimensions, and we tried to understand some intuition of high dimensions, essentially without using any probability theory. And this will be a lot easier actually to understand once we have access to probability theory. And so today, what we're going to do is just the very basics of probability. Right? A lot of the probability theory we're going to use, we're just going to present the very basics. Right? So this will be essentially about probability. Okay? And so, let's say we have a random variable x. Right? To be interested in things like, so you have a random variable. Sort of the first question you should ask about it is what's its mean, what's its expectation, right? Now we might want to measure, how close to its expectation it typically is, or what the amount of deviations, right? This is measured quite well by the variance. It is sort of the most important properties of a random variable. Okay, there'll be other important tools, right? So the variance will control, basically the second moment or the centered second moment, right? There's another important tool in probability which is able to control other moments, right? And this is the so-called moment generating function. So let's say that the random variable is centered. The moment generating function, which may or may not exist, but for some variables that we consider will exist, this is a very important function, right, for t some real, right? Because effectively this will control now essentially every moment of the variable x, right? Because we have, if you take the Taylor expansion of exponential, you essentially get every moment, right? This is a generating function for every moment of x. Okay, now just a few other, definitions that will make an appearance, right? So the LP norm of a random variable is exactly what you would expect, right? Is the pth moment of the random variable to the 1 over p, right? And of course, the L infinity norm is just the supremum. Okay, so it's the essential supremum of the norm of x, right? And in particular, L2, right, is particularly important because it's an inner product, right? We can define an inner product. If we have two random variables, x and y, then the inner product between x and y is just the expected value of x times y, right? It has a norm. I mean, it's the same thing. It's just, right, the inner product of x with x. So the L2 norm squared would just be, right, the expected value of x squared. Okay, and so this means it's effectively, in a Hilbert space, right? It has an inner product, a norm. Now, there's a few other things, right? So I'll just write a few of the definitions. I'm assuming you've all have seen this before, but just sort of set notation, right? What we call the standard deviation, right, is just the square root of the variance. So it's really just the L2 norm of x minus this expectation, right? And we also imported this between two random variables, how much they correlate, right, or their covariance, right? So the covariance of x and y is equal to expected value of x minus expected value of x times y minus expected value of y. Okay, and so now, let's try to see, some very simple propositions, right? Okay, so just one more definition that sometimes makes an appearance. With this, I'm more setting notation than anything else. Okay? If you have not seen these things before, you should definitely pick up a book of probability theory and read up on this. Right. So if you have a random variable, a very natural function to define is what's called the cumulative distribution function. So it's just a probability for a value t is just a probability that x is smaller or equal than t. Right. It essentially tells you everything about the random variable. Right, and okay, very simple proposition. If you haven't proved this before, you should definitely try it. Right, if x is bigger or equal than 0, then the expected value of x is equal to probability from 0 to infinity, the integral from 0 to infinity of the tail, what we call the tail. So this we call the probability of the tail, right? It's the probability that x is bigger than some value t. And if you haven't not proved this before, You should definitely do it. So this is homework, and draw a picture. It really helps. I think once you draw a picture, you see the proof of this. Okay, so another object we're going to need is conditional probabilities. So conditional probabilities is it's just you take the probability condition on something, right? So let's say I take a number from 1 to 10. I ask, uniformly say, I ask, what's the probability of seeing 2? Well, it's a tenth. But what if I ask, what's the probability of seeing a 2 condition on the number that we see being even, right? And we know that we're just taking either 2, 4, 6, 8, or 10, and so the probability becomes 1/5, right? So if E is an event, right? If we have E an event with non-zero probability, right, then we can define, the probability distribution condition on E, and very important too, we can define the expected value condition on E. Right, so condition on something, what's the expected value of my random variable? Okay, so I'm assuming you've seen all these definitions, but just sort of to set the notation. Now let's prove our first theorem. Right, so we'll be very interested in understanding, right? This sort of goes back to the lecture before this one, right? That we want to sort of claim that there were blessings in high dimensions in a way, and the idea was that random variables in high dimensions become very, very predictable, or some of them at least become predictable in certain ways. And what does one mean by a random variable becoming predictable? Right? It should be that it's somehow close to its expectation. Right? That if you compute the expectation of a random variable, then the random variable should be very, very close to it. Right? And this is what we call concentration inequalities, or concentration of measure. Concentration of measure, right? That usually is obtained via concentration inequalities. Right, this is the idea, okay, intuition, right? Random variables, in high dimensions, we'll get to it in a second, are often, or are sometimes, okay, so sometimes as in like important times, but sometimes close to its expectation. Or let me rephrase that. Let me say this. Some random variables, maybe that's better, tends to be very close to its expectation, or to their expectation. Okay, so let's see the first form of sort of inequality of this type. It's going to tell us that the random variable can't be too far away from its expectation. So the first instance, which I'm assuming you've seen this theorem before. This is one of the most, it's sort of one of the nicest theorems in probability. This is known as Markovs inequality. Okay, so Markovs inequality says the following. Take a non-negative random variable x. Okay. Then it says, it says the probability that if its expectation is small, then the random variable can't be very likely to be very large, right? If the random variable was very likely to be very large, because it can never be negative, there's nothing that could make it mean small, right? If you have that very often it's very large, then to make the mean small, you would have to be also very negative once in a while at least. Since it's not negative, this can't happen, right? So if the expected value is small, then the variable can't be very likely to be very large, right? So the actual inequality, that's the intuition of what I just stated. The actual inequality says that the probability that x is bigger or equal than some value t is always smaller or equal than the expected value of x divided by t. And the proof of this is exactly what I said, right? We just have to make it into an argument. Okay, so let's see the proof of this. Okay, proof of this. Okay, let's just write the expected value. Let's split the expected value of x, right? in the part condition on being smaller than t and the part condition on being bigger or equal than t. Okay, so expected value of x, right, the mean of x, is what? It's equal to the probability, right, that, okay, I've been using this like this, the probability that x is smaller than t times the expected value of x condition on x being smaller than t, right, plus, the probability that x is bigger or equal than t, right, condition times the expected value condition on of x condition on x being bigger or equal than t. Okay, but now let's look at this again. Okay, well, I know that the probability of x being smaller than t is a probability of something, so it cannot be negative. The random variable is non-negative, so this expectation can't be negative either, right? So this for sure is bigger or equal than 0, right? Okay. On the other hand, this is the expectation of x condition on x being bigger or equal than t. So I know for a fact already that x is bigger or equal than t, right? And so, of course, the expected value of x condition on this needs to be bigger or equal than t. Right? There's no other way around it. Okay, and this basically we just proved the inequality, right? We just need to now collect terms, not even many terms, right? Because this means that expected value of x, right, is bigger or equal than 0 plus probability of x being bigger or equal than t times t, right? I just move this around. What do I get? I get that probability of x bigger or equal than t, right, is smaller or equal than expected value of x divided by t, and I'm done, right? QED. Okay, so that was easy. You can see this is sort of extremely weak. It's not using anything about the random variable besides non-negativity and expectation. But at least we know if we have a non-negative random variable, it can't be, we can control the probability of being really, really large, right? If you think of x as some kind of amount of error or noise or something, if you can control this expectation, you can already control sort of the probability of disastrous events of this being too large, right? But can we do better? Okay, let's say that we don't want necessarily x to be, we want to say things about random variables are not necessarily negative. So let x be just a random variable, right? Let's say x is a random variable with variance, right? So x, random variable with variance, such that expected value of x minus expected value of x squared exists, right? So, okay, it has a variance. This is just equal to the variance. Okay, so it's a random variable that has a variance. Okay, so now it has some expected value, right? It should definitely, of course, also have some expected value. And I could try to say something of the style, right? This is certainly intuitive, that if I have a random variable, if it has small variance, then most of the time it should be close to its expectation, right? So intuition. Okay, if variance of x is small, then most of the time, okay, before we start writing theorems and proving theorems, we should get a sense of what it is that we're trying to say and why should it be true, right? So if the variance is small, then most of the time x should be close to expected value of x. This feels very reasonable, right? Because the variance is actually, measuring the deviations, right? So can we get an inequality like this, right? So can we prove such a statement? Okay, and so let's do that now, right? The answer will be yes. And how do we do this? Well, now that we have Markov, it's actually very easy, right? We have to control the size of the random variable x minus its expectation, say squared, right? Because we want deviations. We want it to be from to the left and to the right, right? So the idea So idea is use Markov on the random variable x minus expected value of x squared. Okay, it is non-negative, right? Good. So it is non-negative. Okay, check. It has an expectation, which is equal to the variance, so we can use Markov. Okay, so by Markov, what do we get? We get that the probability, sorry, that the probability of x minus expected value of x squared being bigger or equal than some t. Okay, let's use another letter u because I want to make, I want to do a change of variables in a bit. Is smaller or equal than expected value, right, of x minus expected value of x squared over t. But this is just the variance of x over t. Over u, sorry, yeah. Okay, but now we can make u be t squared, right? We can write u equal t squared, right? And now we really get just that probability of absolute value, right? So the deviations of x being bigger than t, right? It's the same thing, of course, as the probability of x minus expected value of x squared being bigger or equal than t squared, which is u, right? And so this is smaller or equal than variance of x divided by t squared. Okay. So now we see that the probability of the deviations, we can get a decay that's quadratic on the deviations. Right? And this will be quite important. Right? Before in Markov, first of all, we now don't need the random variable to be a negative, right? But when we were doing Markov, we only had a quotient that looked like 1 over t. Now we get t squared, which is a better probability. But it's a reasonable question to ask now, can we do better? Right? Can we get better control than t squared? Right? And it's a reasonable question to ask, why would we care about getting better control? Right? If t is a little bit big, 1 over t squared is so large already, like why should we care? And I'll try to convince you that indeed we should care very much. And the reason is, so I'll give you sort of a homework example for you to try out, but to think about it, it's, you would say, okay, let's say that you're controlling here some random variable. You want to make sure that it's close to expectation because that's sort of what you expect the behavior of some noise in some data or behavior of some algorithm in high dimension or something like this. And you say, okay, if I can get something much smaller than 1 over t squared, then I make sure that the probability of making a mistake or having error or something like this is much, much smaller. Okay, sure. But if your probability is small or very small, it probably doesn't make much of a difference. The place where it makes a huge difference is that in many, many places, we're going to have to control many, many random variables at the same time. So we're not just going to control one variable like the noise or the error, but we're going to control many, many possible errors or noise in many, many possible directions at the same time. So we're going to have to union bound. The probability of seeing an error will be smaller or equal than the sum of the probabilities of each of the errors showing up, right? Like a union bound. And oftentimes we're going to have to control exponentially many things at the same time. Right? And if a probability only decays quadratically, we're going to run into trouble. So actually, we're going to want the probability to decay exponentially in many, many settings. Okay, so let's try to let me show you an example of a much stronger inequality that we can get. Right. So one idea is to use the moment generating function. Right. We'll use the moment generating function. Okay, so let's do a little bit of calculations. Let's say that we have mu equals expected value of x. And now let's take let's imagine that there exists a constant, right? There exists a constant constant C, let me write C, or B and 0 constant, such that, the moment generating function of the centered random variable, most of the times when we use moment generating functions, we'll take them to be centered. Right, let's say that this exists for all lambda inside the interval from 0 to b. Then we can use Markov in this exponential, right? Because the exponential of something is always net negative, so let's use Markov. Okay, so let's use Markov. Let's use Markov on e to the lambda x minus mu, right? For lambda in that equation, what do we get? We get that the probability, right, of e to the lambda. Okay, so let's do it this way. We get that the probability of x minus mu, okay, being bigger or equal than t. Okay, let's say we take lambda, this is of course lambda, sorry, right? We take lambda positive, okay? Now, or actual positive. Now the probability of x minus mu being bigger than t is the same as the probability, right, that e to the lambda x minus mu is bigger or equal than e to the lambda t. Right, because exponential, since lambda is positive, exponential is monotone. Okay, so far so good. Right. Now, by Markov, right? So by Markov, this is smaller or equal than the expected value, right, of e to the lambda x minus mu, right? The centered moment generating function, or the moment generating function of the centered variable, divided by e to the lambda t. So now I'm getting an exponential, right? Exponential dependency on t. And generally, when we use this method, we optimize, we then optimize for lambda. I mean, this seems very vague or like not so explicit because I'm giving sort of the idea of a general method. Right? But I'm going to use it now a couple of times. Right? We're going to use it to understand the tails of a Gaussian, and then we'll use it when we understand sort of variables in high dimension. So in particular, sums of independent random variables. Okay, and this is generally known as Chernoff's bound, like this method or Chernoff's method. The idea of taking, using Markov and an exponential and getting an exponential dependency on t via the moment generating function. Okay, so let's do an example. Okay, let's work out an example. Okay, so let's do an example. Okay, let's look at a Gaussian. X is drawn according to a Gaussian. So mean mu and variance sigma squared, right? So this will be what we call Gaussian. Okay, let's see if we can get a decay on the tails of the Gaussian, right? So we're going to prove, proposition. Okay, I should say what is the density, right? The density of this Gaussian. Let me just write it down. So we're going to use it in a second. It's the density phi t equals 1 over 2 pi sigma square exponential of minus t minus u squared over 2 sigma squared. We want to control, right? So the mean is mu, the variance is sigma square. We'd like to say something of the type, well, the probability that's much bigger than its mean is actually very small. Right? And we're going to be able to do much. Chernoff would, of course, give us something already. Or, sorry, Chebyshev would already give us something. Right? So, okay, I should have said the name of this, right? This is Chebyshev's inequality. Right? So Chebyshev would give us something, would say that the probability, right, of being much bigger than the mean is something like sigma square over the distance squared to the mean. But we're going to be able to get something exponential, right? And that's going to be quite, potentially a lot more useful. And so I'll write now the actual result we're going to get, and then we'll prove it. Okay, so proposition, the probability that x is bigger or equal than mu plus some deviation t is going to be smaller or equal than e to the minus t square divided by 2 sigma square. This is much stronger than getting something like a 1 over t square probability of deviations, right? This probability here is not just exponentially small; it's even exponentially small on the square of the deviation. Okay, so let's prove this, and we'll do this using the Chernoff method. Okay, so without loss of generality, so that I don't carry around as many parameters, let's say the Gaussian is standard. Okay, so mu is 0 and sigma square is 1. Okay. This is called a standard, standard Gaussian. Okay, if the Gaussian, well, the mean, of course, is just it's easy to see that if you prove it for mu equals 0, you prove it for this because the Gaussian is just shifted, and with the sigma. Assuming the sigma is 1 is also not hard to see that it's without loss of generality, right? You just sort of scale x and scale t, and you'll scale t exactly by sigma, and so everything sort of cancels out here. Okay? So if you prove it for standard Gaussians, we prove it for everything. Okay, so we're going to use the Chernoff's method. We're going to use Chernoff's method. So we have to control the moment generating function, right? So we have to understand expected value of e to the lambda t. Okay, so let's compute this. Right, expected value over the, x, sorry, right? So x is drawn according to a standard Gaussian, and we have to understand its moment generating function. Okay, so let's compute, let's do that. Okay, so it's equal to 1 over root 2 pi. Sure, so far so good. Right, minus the integral from minus infinity to infinity, right? I'm just going to use the density. Okay. Sometimes it's called probability density function. Okay, so what do I have here? I have, well, e to the lambda x, the thing I'm taking expected value of, times the actual, the density. So e to the minus x squared over 2, right? Because sigma is 1 here. Okay, dx. Right, and this is what I need to compute. Okay, so let's just do a bit of calculations. 2 pi minus infinity to plus infinity. Right, so I get e to the lambda x minus x squared over 2. Okay, so far so good. Dx. So now let's do right. So now let's do the completion of the squares, right? This is a very standard technique to work out these integrals. Okay, so what this is the same as doing 1 over root 2 pi, right? Now minus infinity to infinity of, and now if I want to complete the squares, right? This is, I'll just do it, and I'm sure you've seen things like this before. Okay, let me make this a bit more suggestive. Now for what the steps we're going to do next. It's e to the lambda square over 2. Right, because let's see what this is doing. So, I have a minus x squared over 2, which I get over there. I have a plus 2x lambda over 2, so I get a lambda x, which is what's over there. And I get a minus lambda squared over 2, which cancels with this one. Okay, so far so good. Okay, the lambda I can take it out, so I have e to the lambda square over 2, right? Times 1 over root 2 pi of the integral minus infinity to infinity of e to the minus x minus lambda square over 2. Okay, now this still looks like a pretty, nasty integral to compute, right? But it's not so easy to, it's not so hard to see that this is just the density, right? This is just the integral of a density of a Gaussian that has been shifted, right? So this is just the integral of a density of a Gaussian that has been shifted by, right? That's just been shifted by lambda, right? It's like taking a Gaussian with mean lambda, right? So this integral is for sure one, right? It's the exact same thing as taking the, the integral of the probability density of a Gaussian with mean lambda. Okay, I mean, of course, including the dx. Okay, so then this is equal to e to the lambda square over 2. Okay, so we've computed the moment generating function of the Gaussian. Great. So now let's use it. Okay, so now let's use what we saw for Chernoff. Right now we can use Chernoff's method. Okay, and what do we get? We get that the probability, right? So the probability of x being bigger or equal than t is smaller or equal than e to the lambda square over 2, right? The expected value of the moment generating function divided by e to the lambda t. Okay, so let's now, we have to optimize for lambda, so let's put everything together. So this is lambda square over 2 minus lambda t. Now, what is the right t? Well, what is the right lambda, right? So if lambda grows very much to infinity or very much to minus infinity, this gets really big, so that's not good, right? So this is a parabola that's sort of convex, so we have to take the derivative, right? We just have to take d lambda, right, of lambda square 2 minus lambda t equals 0, right, to pick the optimal t. So to pick the optimal lambda, sorry, so lambda optimum is what? Right, so if I take the derivative, I get lambda equal minus t equals 0. So I just have to pick it equal to t. Okay, so let's do that. So now for lambda equals to t, we get that this is equal to exponential of, right, t square over 2 minus t square. This is just equal to exponential of minus t square over 2. And this is exactly what we wanted to show, right? If you look at the proposition, this is when sigma is 1, this is exactly what we wanted to show, right? Now we get a decay that's much, much stronger than what we had before via Markov or via Chebyshev or anything of this type, right? Now, one thing that will sometimes make an appearance in the course is because, what did we use here? In order to get such a good tail bound, the only thing we used was the fact that the moment generating function was given by e to the lambda square over 2. So this will be quite important, and we'll have a definition for this. So if x, so like definition, right? If x is a random variable, such that there exists sigma bigger than 0, for which, right, such that the following holds. So let's take mu to be the expected value of x, right? Then we have that the expected value of x, right, the moment generating function of the centered, of the centered random variable is bounded by e to the lambda square sigma square over 2. We say x is Subgaussian. Okay, and the point is basically if x is Subgaussian, it means we can carry the proof that we just carried, and so the tails become of the size of double exponential of what we call Gaussian tails, right? So exponential of minus the square. Okay, you have to keep track of this other parameter. But so whenever you can show that a random variable satisfies, its moment generating function is bounded by the one of a Gaussian, we call it Subgaussian. And essentially this allows you to, it's clear that it allows you to extend the proof from above, but it will allow you to extend many, many arguments. So it's a very important definition. All right, thank you.